Okay, welcome everybody. We got about halfway through this, so shouldn't have any issues wrapping this chapter up today. Quick announcement, I am about halfway through grading the essay questions on the fourth exam. I hope, I'm not making any guarantees, but I hope to get all of them wrapped up this afternoon. We will see. If not today, tomorrow for sure. So, questions or concerns about any of that? Okay. So we left off with this slide talking about some of the activity of natural killer cells. And in this instance, we're looking at one that's targeting one of our own cells that's been infected by a virus. They also have the potential to look at and target cancerous cells. So surveillance of our own body are really what the natural killer cells are doing, trying to see if there are any potential issues. And they detect those issues based off of our cellular fingerprints, these major histocompatibility complexes. And as I said last time, nucleated cells have this type 1 complex on them. There are some other proteins that we could see on some immune cells that we call MHC2s that help with communication, trying to tell other cells what's going on. But trying to say, hey, this is me, that's the MHC1 molecules that are on the surface of these nucleated cells. And when this marker declines, when those MHC1 complexes decline as a result of either a cancerous or virally infected cell, that's when those natural killer cells have the ability to recognize that there's a problem and try to deal with it. And so a lot of the idea is the destruction of those cells. And there are numerous mechanisms that the natural killer cells can do to stimulate the demise of those cells. So apoptosis, a mechanism where the cell basically blebs off into little pieces as it self-destroys. Perforin, here we can see a handful of natural killer cells, and they've got some granules in there, digestive enzymes, and perforin basically perforates, as the name hopefully implies, pokes holes in these cells and helps to cause those cells to lyse, all right? Lots of activity with these natural killer cells just doing normal surveillance, all right? And the perforin is a good mechanism that they harbor within their arsenal of agents for destruction. So shifting over, monocytes, we've talked the littlest bit about these last time as well. Monocytes are cells within our blood that in turn will leave the circulation and migrate into the tissues, differentiating into macrophages. And there are handfuls of different types of macrophages, all similar sorts of roles, but basically giving them different types of names for the specific organs that they may take up residence within, all right? So in this image, we've got a handful of different things in this blood smear. The PMN or the neutrophil that would be pretty common to see them in high levels in a normal blood smear. And we also have in this image a handful of monocytes that we are looking at, and some other stuff, right? A few other cells, lots of red blood cells, but it's the monocytes really that we're thinking about, all right? So as opposed to the granulocytes where we can see the stippling or the speckles in the cytoplasm of those cells that are the different types of digestive enzymes, Monocytes are what we call agranular. Their cytoplasm looks pretty clear, all right? Not chock full of all sorts of digestive enzymes and numerous lysosomes, all right? So pretty smooth, all right, or clear. There's the littlest hint of some fuzz in there, it sort of looks like, but it's nothing like what we see with this neutrophil with all sorts of little speckles inside, right? So in a blood smear, the macrophages are bigger. They're all, pretty close to the same size, but you can see comparison-wise, monocyte versus a neutrophil, quite a bit bigger, all right? This guy right here, maybe this one over here as well, although this looks a bit darker. These might be some lymphocytes, T cells or B cells. In a blood smear, you wouldn't really be able to tell the difference with them, but they typically have a gigantic nucleus that virtually looks as if it's filling up the entire cell with hardly no cytoplasm, right? And both of these look very similar like that, all right? I mean, it's a little darker over here, but they sort of have the same sort of an appearance, I feel like, right? So that's the idea, right? This one up here is also probably another neutrophil, looks kind of convoluted, and the granules look kind of neutral staining, kind of light lavender sort of color, right? And then this guy likely a little platelet, all right? So enough of that overview of all of those cells. Here's an image of a handful of different macrophages as they have made their way out of the circulation into the tissues. And at this point, they're doing surveillance in a kind of a similar idea as those natural killer cells moving through looking for things. But in these circumstances, the surveillance isn't really looking at our own cells. It's looking for foreign invaders, for potential pathogens. That's what the macrophage is really trying to do, is it's moving out and doing this surveillance. It's trying to seek the foreign invaders, not our own cells. However, there are some potentials with antibody responses where maybe antibodies may link up to some of our own cells that may trigger macrophage activity to come in and destroy, right? So it's not like they completely leave our cells alone, but they need some sort of trigger to actually deal with it that's a little different than what the natural killer cells can do, right? So there's lots and lots of stuff we could think about to try to describe some of these immune processes. I posted a couple of videos on Moodle about, well, one about complement and kind of another one that's a bigger overview of immunity and the cells that are participating in these reactions. There are lots of things that our body may be coming in contact with in that world around us, and in a wound situation, as we've got right here, we've got a cut that, however, it breaks the skin and introduces some organisms into this wound. So our green guys are the pathogens, right? And this sets the stage for all sorts of activity to be going on. We also could be, and we're not going to, but we could be thinking a little bit about tissue repair mechanisms that could be going on to help start the healing process after this wound has been created in our body, right? So lots of stuff happening here, all right? So leukocytes are white blood cells, respond to all sorts of different chemical signals that may be released from those microbes that in turn stimulates these immune cells to recognize, to kind of sniff them out like a bloodhound, I sort of imagine, all right? So here we could see our skin, the wound, the organisms getting in, and within the tissues, this big globby guy is a macrophage that recognizes this based off of some of the chemical signatures, and it engulfs it. It phagocytizes it, pulls it in, and destroys. And then we're going to see some other stuff. Really, the focus of the next chapter is what happens after this occurs, really. All right. So other things can start happening as we see some of these chemical messengers and messages, not only from the bacteria saying, here I am, but from macrophages that are saying, look what I've just found. That stimulates other things to start responding. Some of these other little speckles that we see throughout here, as we move to this next image, we can see C5a. This is one of the components of our complement system. So one of these proteins, and in turn, complement has some activity within this as well. All right. So keeping that in mind. Some of this activity as complement starts to get activated is to stimulate, basically sending out the alarm to stimulate cells within our circulation to move out of the circulation and into the tissues and start the destruction process. All right. So the leukocytes, these white blood cells, lots of neutrophils, but some other players as well, other granulocytes, but a lot of neutrophils are going to be responding to this. And they move through the capillary by diapedesis, by basically crawling through in between these cells. They squish through there and get into the tissues, right? Neutrophils, I mean, there's a boatload of them in our circulation. They are being generated really pretty rapidly. And when they respond to something, it's basically they're going to take one for the team, and they will pull in this foreign organism, this bacterium or whatever it might be, phagocytizing it, and destroying itself in the process. All right. And lots of inflammatory reaction can be the result of some of these neutrophils and other cells that are coming in to mop stuff up. And pus that we see can be the result of a lot of dead neutrophils, dead organisms too, but a lot of our own cells that have sacrificed themselves in the hopes that they can truly get whatever these green guys were coming in to get them under control. All right. So the neutrophils, as they come in to respond, can release some cytotoxic chemicals. And this in turn can extracellularly kill these microbes, along with the fact that they can pull them in and destroy them that way as well. All right. So all of this stuff helps to destroy and start mopping up those destroyed cells to clean up, all right, all of this issue in the first place, all right, if things are functioning properly, all right. So this could be our macrophage, this phagocytic cell that has a handful of different potentials to seek out things, all right. We talked about the natural killer cells looking for the MHC1 molecules on our own nucleated cells. But the macrophages, they're doing different surveillance, and they're trying to sniff out bacterial or other microbe signatures. It's not just bacteria, although a lot of what we're showing here really is bacteria stuff. It could be other substances as well that they may be able to recognize, right? So on our phagocyte, there are pattern recognition receptors, these green guys, all right? And there's all sorts of different types, all right, that can recognize different substances and stimulate this phagocytic cell to respond, all right? It's got the ability to sense lots of things that we would say are foreign and potentially bad news, right? So the stuff that they're really trying to sense out, we call PAMPs, which are pathogen-associated molecular patterns. It's not the same as the MHC1, but it's the same idea, right? It's a specific signature of molecules that it can recognize, right? So in these examples, we can see stuff here, like receptors looking for lipopeptide. So like an outer membrane of a gram-negative bacterium could be detected that way. Lots of bacteria have flagella, and potentially recognizing flagellin will lend to these phagocytic cells recognizing there's some motile organism that's made its way into our tissues, right? And then peptidoglycan, components of cell walls of the bacteria, all of these have some potentials to be recognized, all right? Here we can see this bit on the inside in this vesicle. This receptor, it technically would have been on the outside of the cell, but we have pulled it in, all right? So this is a nucleic acid receptor. So it's something that could recognize components of these bacterial cells, their nucleic acids, and in turn, maybe recognizing some details from a cell that's already been destroyed, maybe from a neutrophil or something else that's caused it to explode. Now the nucleic acid is free floating, and these receptors can pick that stuff up. I'm getting signatures of DNA out here, and I shouldn't be, and we should start doing something about it, all right? So the nucleic acid receptor would have been on the outside. All of these would be initially on the outside of that cell, studded in the membrane, and then once they make contact with whatever, it stimulates this phagocytic cell to invaginate or engulf whatever it is it's linked up to that receptor, and it pops it to the inside. Now we've got a little vesicle that's harboring whatever we brought inside, and we'll call it a phagocytome, all right? Little food vacuole we could think of, all right? But really, we're doing more here than just thinking, I want to eat this stuff, right? We're doing the show and tell to basically say, look what I found, and let's do something about it. The do something about it, it's going to come in a little bit, all right? So upon recognition of this, we would see this phagosome fusing with a lysosome, call that a phagolysosome or a secondary vacuole that helps to aid in the destruction of whatever molecule we've popped to the inside. That in turn, there's all sorts of other things that provide a stimulus for this macrophage or phagocytic cell, typically macrophage, but it could be a dendritic cell as well that might be doing a lot of these details. Basically, after this has occurred, we can start sending out signals, interferons or cytokines, other cytokines that serve as messengers to other types of cells or more macrophages to come in and start responding. So lots of things, right? And it's more than just bacteria that we might be thinking about targeting in these circumstances. So this similar sort of an idea as we were just thinking about, in this case, and pulled in, right? The macrophage recognizes it and recognizes something, right, on this surface of this bacterial cell that stimulates it to link up to it and engulf it, right? So the bacterium phagocytizes, pulls it to the inside. Here it's within this vesicle and our bacterium on the inside. Fusing with that lysosome, like I described just a second ago, creating this secondary or phagolysosome where the digestive enzymes are dumped onto that bacterium and destroys it, right? There are all sorts of things after this has occurred that happen, and some of it gets dumped to the outside as waste, like taking your trash out to the curb, right? But there's other stuff that happens as well, right? And we will touch on a bit of that a little later on as well. But some of these particles might be something that could stimulate our body to respond. And this macrophage, after it has fed on or engulfed this foreign entity, whatever it could be, we're going to show pieces of that on the outside of that macrophage, right? And that's where those MHC2 molecules come into play. Macrophages and some others, but macrophages have a lot of these MHC2 molecules that can be showing little pieces of this bacteria, things that are likely going to stimulate a response from other cells within our body, and hopefully thinking stuff like antibody production. All right. So that really will be what we think about in the next chapter of material when these macrophages start doing this show and tell and stimulating some of these responses. I like this slide because it's got a bit of parasitology in here, and I think it's pretty awesome. But I'm also I'm a little bit there's a little of it that's not 100% accurate. All right, that's okay. All right, I think the picture of this guy is pretty shocking, and so maybe good to show it as this, but it's not exactly 100% accurate with what we're talking about right here. All right. Cutaneous leishmaniasis is a parasite, Leishmania, and this one, Leishmania tropica. There are a handful of species of these Leishmania parasites that can cause various types of disease in people. Cutaneous forms, and also some visceral stuff. So like some organ involvement that's definitely more of a concern. Not that this doesn't look like it's a concern, all right? But it's a little bit wrong, all right? This image of this individual isn't really cutaneous leishmaniasis, all right? Really what we're looking at in this circumstance is an individual that has the visceral form of leishmaniasis, so organ involvement, not skin involvement, all right? But you're like, wait a minute, what's up with this skin, right? The issue with this individual is the result, and lots of these types of parasitic infections are pretty stinking difficult to treat. The course of treatment could be months or a year worth of therapy. That's a problem, all right? People have trouble taking antibiotics for 10 days, right? So thinking that you're gonna be diligent and take all of your medicine exactly like you should when you have to do it for months, there's going to maybe be some issues, right? There's also potential issues with, maybe you miss a dose or something like that. So the level of the drug within your body, if it's not sufficient, that can lend to problems as well. Even if you're trying to do as good as you can, but yesterday I forgot, right? Or whatever it is, and it causes the dose to decline a little bit. What we're really looking at with this guy is called post-Kala-azar dermal leishmanoid. That is a huge mouthful, all right? And really, it's a skin manifestation of the visceral form because you didn't take your drugs properly, all right? That's what's up with it, all right? The cutaneous forms of leishmaniasis have big, like open ulcerated wounds. That's the cutaneous phase. And these suckers aren't like that, all right? These are kind of big, sort of wart-like looking things, all right? Not the same thing as the cutaneous form, all right? But for our purposes here, it, shock and awe, right? This type, you're like, whoa, holy cow, right? And deep down, it is still a huge concern, all right? From what I gather, this guy, if he starts taking his drugs properly, so he gets back on them, or potentially the dosage wasn't right in the first place, and when we get all of that stuff figured out, apparently this stuff goes away, all right? And you don't have any hints of this, but there are definitely issues, all right? So that's my little soapbox talking about that, because it's sort of true and sort of not, all right? One thing that I think is super awesome, also a little bit disturbing, Leishmania can live inside of the macrophages that should be doing this killing. Brilliant strategy for some of these organisms. Tuberculosis is another pathogen that can live in the macrophages, and there's a few others, all right? These guys, when they get into the macrophage, cause that macrophage to basically shut down. They don't destroy or digest these microbes that have got in there. They basically shut down that process and are immune to the destruction properties of those cells. They live inside of them, replicating and destroying those macrophages. A brilliant way to avoid the immune response would be to live in those cells that are trying to kill you in the first place. You can't kill me, and I'm living right within you, and then I kill you, right? That is crazy. So this macrophage has a bunch of amastigotes. These amastigotes are a cycle of this parasite that we would find within us, all right? So it's the Leishmania parasite, but the stage of it is called an amastigote, all right? So it's full of these amastigote cells inside of the macrophage, all right? And it doesn't matter if we're talking cutaneous or visceral forms of this parasite, we would see this in a blood smear, all right? There's also potentials to see some free-floating amastigotes in the circulation. If these macrophages had ruptured, releasing them, they've got the ability to kind of migrate around and try to infect other things. And in this circumstance, we can see it in a blood smear with some red cells and the like, all right? So impressive, disturbing, and kind of awesome, all right, that they can live in those cells, right? There are ideas about, a handful of different types of pathogens like that, you wonder, how can we really target these things when they're living inside of some of these cells? Macrophages are pretty good at picking up things, right? And so one strategy for some of these parasites or organisms that want to live in the macrophage is to use some sort of a drug with a carrier molecule that macrophage will see as foreign substance. And it pulls that foreign substance in, but not only does it pull that carrier molecule in, it pulls the drug onto the inside of the macrophage as well. And now we've got our treatment delivered right inside of the macrophage, and we could destroy those amastigotes or other organisms inside, all right? Pretty good idea, but it's also difficult, all right? Trying to get that to, truly function perfectly. So it's not the same image, but it's sort of the same image of this wound that had been created from however with the organisms getting in, all right? Just showing a few different players in this instance. So mast cells, they've migrated to the tissues like macrophages, right? And in this wound, mast cells can start the process of inflammation as they recognize some of these signals from the microbe. The mast cells like, wait a minute, and it starts dumping histamine that stimulates some of the inflammatory response. So we can see initially our vessel over here normal, if you will, all right? And the histamine, as it makes its way in, causes vasodilation. So now we've got increased circulation to this area. We've got increased blood flow. And with that, we've got a greater opportunity for more cells to be arriving in this situation, all right? Lending to enhanced diapedesis or movement of the white blood cells out of the circulation into the tissues. And so here, these, phagocytes, neutrophils, start showing up and dealing with these processes. There's other cells as well. I mentioned that before, but a lot of this initial activity is neutrophil driven. Eosinophils and basophils, other granulocytes may also be showing up. Eosinophils, although they are classified as these phagocytic cells, they're not really pulling things in. They do more extracellular killing. They dump their digestive enzymes to the outside. Basophils do a lot of stimuli like the mast cells and start releasing a lot of different chemical mediators, trying to detect what's up and send out some signals like the mast cells saying, let's get as many troops here as we can. So there's a lot of players that are really trying to get involved. The previous image like this was showing some macrophage doing this and sending out signals to stimulate other cells. This just a different potential. Seems to make sense that it would be wise to have more than one way to get all of our troops stimulated to respond, right? So mast cells can do some of this, macrophages, complement proteins as they start getting cleaved, all of these different avenues to get to the same end goal, the demise of these pathogens, all right? And we haven't even started talking about antibodies yet, all right? All of these things are trying to work together to truly try to get whatever it is that's trying to take hold to not, right, to destroy it so it can't move through that process. So I mentioned TB or tuberculosis just a second ago. This image shows a granuloma. This would be looking at lung tissue where we see this granuloma, a tubercle, all right? And that in turn is, as the name kind of is implying, these granulomatous formations within the tissue, right? There are lots of different potentials for this bacterium to get in and take hold. One of them living in the macrophage gives it a leg up and a true advantage. Part of our response against these bacteria that aren't in the macrophage would be to try to recognize them and try to do something about it. And sometimes one of those mechanisms might be to wall it off, to form some sort of granuloma around it, to surround it and encase it and prevent it from doing anything else, all right? There's all sorts of different types of things that may spur a granulomatous reaction. TB is one of them, all right? So these tubercles are these granulomatous reactions where our body has surrounded the bacteria with material to keep it at bay, if you will. That makes it super hard for any sort of chemotherapeutic agents, any sort of antimicrobials to actually get in there and target this, all right? Free floating mycobacteria could be targeted pretty easily, all right? Inside of macrophages, inside of granulomas, not so much, all right? You really need them to be more accessible for that to happen. And with that said, therapy for tuberculosis is super, super long, all right? Kind of like talking the leishmania just a minute ago. It could be a year or better that you're trying to deal with this, all right? We'll think about lots of tuberculosis in the United States. We definitely have it, all right? But we don't think of it as a huge concern. If we go outside of the US, it's big, big problems, all right? 1.5 billion or better people are infected with tuberculosis, all right? That is disturbing to think about that many people, all right, infected, and some of them with some pretty serious multi-drug resistant strains, all right? So some of that really shows up as a result of non-compliance, right? You flat out aren't taking those drugs like you should be for whatever reason, all right? In some countries, they will pay patients to come in and get their treatment because they think maybe some monetary stuff may stimulate that, all right? Sometimes it works, sometimes it doesn't, all right? Another way to make it work is to throw you in prison, all right? We'll lock you up. If there's non-compliance, you won't take your pills like you're supposed to, we'll put you in prison and then we'll feed them to you, all right? Those other issues with that altogether, all right? Crazy, all right? So that's my little spiel with that. We are nearing the end of this. Here's another parasitic infection. There's a handful of different filarial worms, a type of roundworm that can cause some of these issues. And it's like that guy's face, right? It's another one that I'm like, sort of, all right? There are some issues again with this, all right? But we'll let it go, all right? The chronic edema, the swelling, right, isn't really elephantiasis, although it's oftentimes we just sort of think of it the same way. I mean, you think elephantiasis and you look at this dude's leg and you're like, man, that's as big as an elephant foot. That must be where the name comes from, right? But it's really not, all right? So this, where we see this swelling, really is lymphatic filariasis, where these little worms block the channels in the lymph nodes. So the lymph is your body's drainage system, a one-way flow. And as these worms get in there and cause blockages, the fluid that goes out of your circulation into the tissues, the plasma, right? As we think about all of this stuff, becomes interstitial fluid that drains off, makes its way back into the lymphatic system. But with these blockages, it can't drain. And so it just keeps accumulating. And you get this massive swelling, all right? Lymphatic filariasis is the chronic edema, all right? Elephantiasis is different, all right? Although looking at these appendages, it kind of seems like, well, we'll just call it that, all right? Elephantiasis is an alteration in the skin, all right? And elephant skin is very thick, if we were to see that, thick and kind of crackly looking. That's how your skin appears when we really start thinking elephantiasis. Thickened, cracked types of skin, different, more elephant skin-like, not big honking foot, all right? And that in turn, just a little bit of misuse, whatever, all right? This person has both appendages, both legs impacted. Oftentimes with some of this, it might be one or the other, might be a leg, might be an arm. Sometimes it could be both, but usually it kind of targets one. So sort of an exception here where we see both limbs impacted. So there's all sorts of details, and we will talk about some of this as we get to the tail end of this semester, as we start thinking some of the disease. But a handful of different filarial worms that ultimately get inoculated into us, some of them through the bite of a fly or a mosquito that may stimulate this and these changes. There are some others that may give you this type of manifestation, but also may potentially lend to some blindness because they may be targeting your eyes as well. All right. So we'll hit a little of that stuff later on. Pretty disturbing to, see some of these images, and, typically thinking more tropical or subtropical types of habitats, that these types of infections are more common to find. So we talked about inflammation and some potentials with the inflammatory response to stimulate cells to come in and respond. But another part of a response could be some fever production. So ramping up that thermostat, getting the heat going on, could potentially lend to some inhospitable types of environments for some of these organisms, all right? We like to keep our body at 37 degrees Celsius, right? Homeostasis helps to ensure that we stay at a relative constant body temperature, right? And at that temperature, all of our functions happen without any sorts of issues, right? Enzymes and all of that stuff functions just fine at 37 degrees, right? The mesophilic bacteria, those bacteria that like our body temperature, they might be a little bit more sensitive to some of this temperature, all right? And increasing the temperature just a little bit above 37 might be enough to be pretty inhospitable to some of those microbes and prevent them from actually taking hold or, causing disease, maybe, all right? Really kind of depends on circumstances, but, a little bit of a fever, a little low-grade fever, maybe not that big of a deal, all right? There are all sorts of things that could be some fever reducers that maybe you would take, or maybe you got some kids and you want to, drop that fever down, give them some Tylenol or something like that. They could help reduce a fever, all right? If it's a low-grade fever, maybe it's not as big of a deal. If it's a little kid and they're not complaining about stuff, maybe let the fever go, all right? And that in turn might be a mechanism that's enough to truly drive a wedge in whatever cellular reactions those microbes are doing to prevent them from really establishing that disease, all right? Or it spikes even higher, and now we've got real concerns, all right? Because a high fever definitely can be dangerous, all right? But that's really kind of the idea, all right? There are handfuls of things that may stimulate this mechanism to increase our temperature. So hypothalamus is like our body's thermostat that allows us to kind of regulate our temperature. So there can be some exogenous pyrogens. A pyrogen is a fever inducer, all right? Pyro like fire, right? So some sort of stimulus, lipopolysaccharide, outer membrane of a gram-negative bacteria, pretty good at stimulating this, all right? So some endogenous pyrogens, these would be things like some of our white blood cells releasing some chemical mediators, right? So interleukins, interferon, tumor necrosis factor, all of these suckers are types of cytokines, chemical messengers that can do different things, right? So a couple different interleukins, all sorts of different players that are endogenous, things produced within our body that can ramp up that thermostat, right? So acting on the hypothalamus and stimulating fever production, right? And this, I think prostaglandin is the PGE, if I remember right. So this, another potential mechanism as we take some of the innate response, that's really the idea with this chapter, some of just the mechanisms that our body might utilize to try to prevent infection in the first place. Some inflammation, some fever, unbroken barrier of the skin, all of these mechanisms try to prevent that, but obviously it's not 100% effective. And the next chapter of material, we're going to talk about how we take it a step further and start thinking about different types of responses, cell-mediated and a humoral response. So different cell lines we've already mentioned, but the way that they're functioning a little bit different, right? We typically talk about both of those as sort of separate ideas, but deep down, they really function together, right? Trying to get the best response that you possibly can. So we think of the innate, the actual immunity with cell-mediated and humoral responses, all of these things together really functioning to hopefully keep us healthy. All right, we will quit with that. I'm pretty sure that's my end. Yes. Questions, concerns? Okay. Farewell. Have a great day. I will see you all Friday.